Just this seems insanely loud. So let's turn that down a little bit. And do a quick check. Whoops. The stream is actually live. And then we can get going, I guess. I hope you've had a good week so far, and that you are enjoying your Friday. Yeah, that looks promising. Good. Well, so here we are. I've not had much time for preparations, so let's first make sure that you people can see something by switching my editor to a larger font size. Oh, wait, I forgot to not only switch the UI, but also the editor. All right. That should be large enough. Anyway. So what are we planning to do today, even? Well, we have two previous projects that we did as tutorials. One was a bytecode interpreter, which we wrote here. And so it generates these little instructions structs and runs them. So we have that. We also have a simple parser, which takes some text, tokenizes it, and then parses it and prints the result. Doesn't really do much more. The language right now looks, well, the tokens and things it parses look something like this. And what does the parser do? It parses values, function bodies, function calls, and yeah, of course it doesn't parse that, but it also parses expressions already, I think. One value, variable declaration, function call, expression. Yes. Yep. Okay. So we're already doing all that. And now we need to create our project so it ties those together. All right. So first thing we need to do we need to just create a makefile for it. So we have something to work with. New C++ source file, main Yes. Make sure I remembered how to type. Right. So we should be able to now print a simple message just to see that it's actually working. And this simple message should just be something like this. Now let's see if that is enough. Let's close C-line and start it again, and hopefully that will just make it pick up the CMake lists. Here, does that work? CMake, yeah, seems reading the code, and it has picked up the target. Good. So we should probably be able to just run that. Yeah, parser and compiler 1.0. So we have that works. So right now this is just the usual, sort of just integrating the two bits of code. So here we actually need, and I think I'll just have a peek in my other project here. Where is here, for example? Open as a file, add library. Okay, it's just that. And then, okay, so let's try that. Library, simple parser, internal, add executable. So what I'm doing now is wait, where did the other one go? Add executable. Yeah, target link libraries. That's what I wanted to do. So what I'm just doing is I'm taking the code that I had in my executables and extracting it into a library. So instead of just having a simple parser that contains all the code, I'll create a simple parser internal library that contains the code and an executable simple parser that contains that contains the main file and also links that library. Okay. And we want to do the same thing in our bytecode interpreter. So that way our main application can just link that code without getting a redundant main file. So no magic here. Target link libraries. Internals is what I forgot. Bytecode interpreter should link bytecode interpreter internals. And now we need to get the other file from my other project to see here. Add subdirectory is what I'm looking for, and then I can link to it. Okay, so we're adding the subdirectory simple parser, and then target link libraries, parser and compiler, simple parser. All right, so this is different for, like, if you had a different IDE, you would probably do this slightly differently. Don't worry about this too much if you don't understand it. All I'm basically doing is taking the code that I already have for the bytecode interpreter and for simple parser and make it available. Oh, whoops. All right. Enable auto reload. And let's see what CMake thinks about this now. Looking promising. All right. So now, of course, we should use these. So let's just go into our main file. Simple parser, tokenizer, and simple parser. Include those headers. Using namespace simple parser. And now we have to do the same for the bytecode interpreter. And and include that header. And maybe include instruction as well. All right. That should really be all we need. What is it? Oh, of course. What is, yeah. Let's see, does this, yeah, this also has its own namespace. So, for brevity's sake, make sure we're using that as well. All right. And now, first thing we need to do is just run the parser. So we take what we already have here, the main file, and copy it. And why the heck did I commit garbage here? Okay. So, parser and compiler. And this should be a different path. D C-line projects, I think, is where we are right now. Let's see. D C-line projects. Parser and compiler. Simple parser test MYC. That sounds good. So MYC is just an extension I made up for our programming language. Let's log the file contents to see that it works. And let's log the tokens. And yeah. Then debug print the output. That looks good. And now just run this. Let's see if it builds. No, there is something it's unhappy about. Cannot open file, simple parser internals lib. Okay, something. So bytecode interpreter internals did work. Why didn't simple parser work? I guess I can look here. Simple parser main. Simple parser gets simple parser internal. Okay, that should work. Nope. All right. So what's the difference between simple parser and bytecode interpreter? Where did I make a mistake? Let's put them next to each other. All right. Oh, I already see it. No, wait. I don't know. Simple parser. Simple parser internal. Oh. I wrote internal, not internals. Dope. Why did I say dope and not dope? I don't know. Okay, now they should both build. Yes. And it actually ran the code. Well, it parsed the code. As you see, it grabbed this pseudo script. It printed the list of tokens in it, and it then printed our parsed form so that we know it's a main function with an argument count and argument values, a variable declaration for a double variable named foo, which has the initial value 1.5. And it calls a function printf with a string and does some maths. So we now have created a second project that can just run our bytecode in it. That can parse something, and now we also need to copy over the code from the bytecode interpreter, which is from here, where it has an instruction array, and then it runs it and displays the result. We'll put that in our main file as well. We can close these two on the left. Don't really need to see those. All right. So right now, this is just the parser and then the bytecode interpreter, but nothing that has been parsed actually ends up in the bytecode. That's fine. I just want to see that both languages are in the project. And yes, number printed, it runs a loop. And in the end, it says result is 42. That looks like that code also runs. Good. And so now what we need to do is we need to take whatever this parser generated and actually create sorry, let me close all those tabs first. So, and we need to generate equivalent instructions from that. And how you usually do this is by looping over the parse tree that the parser generates. So we see our parser has a list of m functions. Those are function definitions, and the function definitions contain a function name, a parameter definition, and lots of statements that are the actual code. And a statement has a return type, some parameters, and a statement kind. So it can be a variable declaration, a function call, an operator call, and we also have literals. So we have this tree with all the information about our program. but we should parse it. And we should now generate the resulting code. And how you usually do this is you make this stuff available to the outside. So first, we create a map, get functions. So we create an accessor function. Now, I'm separating this to show you what the responsibility of each part is. So we have the parser from the previous tutorial. We have the bytecode interpreter from the previous tutorial. Those are technically separate modules. Like, you could save the bytecode to disk and then ship a bytecode runner that is just the bytecode interpreter. So that's why keeping them separate is not a bad idea. Now C++ is a little stupid in that regard. So we need to perform operations on each type of node. Depending on... Oh no, actually... Yeah, we can do it fine here, because our parse tree is actually limited in types. So as you saw, we have function definitions, and each function definitions contains parameter definitions and statements, and the statements have a statement kind. And that's the thing we will switch on. Now, if we had designed this differently, a better way to do it in C++ would be to, instead of a statement kind, just have different classes for different types of statements. So we'd have one class for a variable declaration, one class for a function call, one or even several classes for the different kinds of literals, and one class for an operator call. But here it's actually good for us that we don't have separate classes for these. So if you write your own parser, what you could do is you could make separate classes and then put one method on this class to allow you to generate code. So you could add a void generate, void generate code, and then, I don't know, vector instruction output code. And so you could just override this method in every subclass and push back, so append your instructions to these this vector. But the problem, of course, is if you have this split like this here, you do not really want to add code related to bytecode interpreter to simple parser. You would want basically to key off the type of a statement, like we can do with the mkind. So this is actually the better design for splitting it up. But what you could also do is you could write yourself a little helper class where you can register objects based on a type, and then just run. Basically what you would do is, I don't even remember how I did it. Well, anyway, so what you can do, all right, basically what you could do is you could do something like, let's just give us a dummy function so the compiler is happy when I write my sample code. So you could do, so if you have a pointer to a subclass, so imagine we had a statement-based class and we have lots of subclasses. It doesn't matter what's in it right now, there would be a real object in there. A pointer to a real object. You can use dynamic cast to find out if it has the type of a subclass. So for example, you could say, like literal statement. And this would return null if it's not of the subclass literal statement. And so you could create a class that is something like literal statement code generator, and put a method in it, bool process statement candidate. And now here you would say if dynamic cast statement, well, it's candidate, of course, in this case. So if that's a literal statement, then call let's call this possibly process, and then here we would call process candidate. So this, and then what you would do is you would have an array full of code generators. So you could have a base class. Maybe you would make this a templated class. Class statement subclass, something like that. And here you would test for the statement subclass. And then here you would have void process statement sub candidate. And this, and so what you can do is you could, for code generation, just create your own. We had a literal code generator or string literal or whatever, and that's a subclass of code generator literal statement, And then here you would just say white process literal statement candidate override. Oh, and of course you need a base class that the other code could deal with. So let's call it base because we're running out of names. And that just exposes virtual possibly process. You could add additional parameters to that. So this is a fully virtual base class. And here you would actually do the code generation. So for a literal statement, it would be something like instructions. The instructions would probably be passed as a parameter to the process function. And then you'd say push back instruction, something like push string, and the actual text. So something like candidate text or whatever, we actually didn't need the function. And now, well, actually we can use the function. So imagine we had a list of functions, of statements. We got those from somewhere. And now what we could just do is for statement statement in statements. And now we also have a list of code generators. So code generator base. And we've just added every code generator that we define for each type of statement. We just add to this list. And now all we do is we do another loop, code generator base. And now we simply say possibly process, which is the only message this has, on the current statement. And that's all we do to generate code for all statements. And now this will take care of, this here will take care of only calling a code generator for the type it's really for, but you can just create a useful, nice class like this that operates on that type. And we need to do something like this for our case as well, of course. So that's why we don't need to do this because we're not based on the type. We can just say if, just use if on the statements. But it's kind of neat to know that you could do this in a more object-oriented way. Just realized I should probably take a second to announce on Twitter that I'm doing this tutorial because I don't have the bot running today, so it didn't do the automatic announcement. Excuse me. Looking up our bytecode interpreter to our parser. I mean, we're kind of halfway through our time slot by now, but who knows, maybe some people will still come. Okay, so we've parsed this stuff. Now we want to generate instructions. So first, we need an instructions array. So let's call this compiled code. I want to leave the old code array there so I don't have to look up how our code actually works, like the push and pop instructions and things like that, the load base pointer relative stuff for recursive call or something. All of that is stuff that I defined there that I can now just look up here. Okay, so we have an array compiled code and we have everything in our CMake project. And now what we need to do is parser get functions, and that is a map from string to function definition. And now for current function and functions. So this is just, we're looping over all our functions. Oh, right. Of course, since we're looping over a dictionary, we're getting a pair. All right. Does this have to be const? Yeah, okay. That was the problem. Okay. And now we can here basically generate code for each function. So curfunc and compiled code. So let's define another function. I might need more parameters or something. I don't really know that yet. All right. Now this can just look at the values in the function definition. So we have a name, we have its parameters, and we have its statements. So right now, I guess an easy way to start would be to just loop over all the functions. To do, well, actually, no. We know from our bytecode interpreter, if we look here, there is a standard function prologue. So, for example, when we start a function, we reserve space for our local variables. So in this case, this is a loop with a counter named x. So we push 0 on the stack to reserve space for our variable. We also have the base pointer set to some value, and we load all these variables relative to the base pointer, which means base pointer relative 0 is this x that we just pushed. Because remember, this is basically how it works in assembler, but I mentioned that in the bytecode interpreter thing. Every function can call itself recursively, of course. And if a function calls itself, you cannot hard code the slot on your stack, like the address of its variables. So you cannot just assume that x is always at spot 0 and y at spot 1. You have to actually know who has already, like by the time your function gets called, your function, there are all the variables from the calling functions on this stack. And of course, if your function calls itself, then there are the variables from the previous call already on the stack, and it needs a new set of variables to operate on, so the values don't get mixed of the inner and outer call. And so, to allow for this, when you call a function, you note down how large the stack was at the time. And that is the base pointer. And then you reference all variables by saying, well, add 0 to the base pointer, add 1 to the base pointer to get the first and second variables. So that's the short refresher. And so that's what this here does. So it depends a bit on your bytecode and how the instructions work. Usually you might set up the base pointer yourself, or your call instruction might set up the base pointer. So for example here, here we call ourselves with the call instruction. And so if we look in the bytecode interpreter, it's here. Where does it exit? Add in, push in, pop in. There is call somewhere here. Here. So what does that? Okay, it remembers where we have to return to. Base index. What is this? Oh, that's the base pointer, right? It's just an index here. Yeah, right. I remember now. That's why I named it. So it saves so this call instruction does a bunch of work that in some applications that's part of each function. So this one saves the base pointer, saves the return address, so that means the instruction after this function gets pushed on the stack, or rather on a separate return address stack. Doesn't really make a difference for us. And we set the base pointer, the base index, to the size of the stack, so we prepare that for you. And then we perform a relative jump here. So, but what we effectively do is we set the current instruction to the address of whatever function is to be called. So we do all this already for you. And when we return, we undo this word. So this works. So first we pop the return address of the stack again, so that we know where to go. We pop the base pointer of the stack again, and write it back into the base pointer register. And of course we jump to the return address again, which is the main job of a return instruction. So all of these I should have already explained in the bytecode interpreter tutorial, so this is just a short refresher. But hey, doesn't hurt to refresh that. But so the thing is, when you generate code for a function, usually you have something called a prologue, which is jobs that you do, like reserve space for the variables, and then an epilogue, which basically undoes that. So in our case, that would just be, pop that variable off the stack. And I think here, delete x, we just call pop int, and then we return. And the thing is, usually you always want to have the same spot at which all this cleanup happens, and then it returns from your function. So if you look at some typical code, you may have a function that contains something like, if bad thing 1, return -1, if bad thing 2, return -2, and then here we do the actual work, and then we return 0 for success, or something like that, is how a function might work. So the naive approach would be that for each of these, you generate a return instruction here. But actually, the return command is not a return instruction, but rather the code that you generate. What you usually do is at the end of the function, you put a cleanup area. I'll mark this with this syntax, which in C indicates a label, so just a point that you can jump to arbitrarily. And so instead of generating code to return here, you just say you assign to the result wherever that is stored, and you then go to the cleanup area. And you do the same for each of these. So that's effectively the code you would generate. And then here in cleanup, you can do the other cleanup work as well that is shared between all of these. So in this case, that would be, take the variable that you've reserved. And at the top here would be the prologue, where you, of course, would say push in 0 to create X, and this undoes that. So that's kind of what you would do. But those are machine code instructions, of course. I can't really approximate them in C here. But anyway, that's basically what we want to do here. So that's, of course, inside a function in our bytecode. So first thing we would do is so we loop over all the variables that our function has. So auto curvar in curfunc parameters, or param is really what we would call it. And now const, I prefer writing the types explicitly, especially if I then have to modify them. Just because here you see the code and you immediately know what it is. And if you want to look up a new field or something, you can click it. As you saw, don't really need all these. I mean, as you saw here, C-line is actually smart, and if I do auto, I guess I could do const auto. Yeah, it will now show me const parameter definition reference. So I guess we can do that to be modern C++, because my editor will show me the type at least. Okay, and now, of course, we have to do it differently for each type. So carparam mtype. And now C-line should what is the type? Oh, that's actually not an integer. Okay. I have to switch on mtype to get the enum. Create missing switch cases. Okay. And now you see we have all these types that we might have. I should probably look at, I guess we can get away with only implementing int for now. I think int should probably be int32. So what this would do is generate a pushback, so pushback an instruction. And now we have to see what arguments instruction. It has an opcode, parameter 1, parameter 2. Right, and we can peek here. Push int. Yeah, I don't really know. So what does this look at? It looks at P2 is the number it actually pushes. Okay. So P1 will be 0. So we push the instruction. Push int 0. And now I think we had a default value for a parameter definition. Oh no, we don't actually. Weird. I thought we remembered that somewhere. Didn't we, when we ran this, actually get variable declaration? Oh, that's only for variables. Of course, because it's an argument. So I'm doing this wrong anyway. So here's the thing. I was doing it wrong, of course, because this is not. So the parameters, of course, are already on the stack. We don't have to do the code I wrote is not related to the parameters. Right, variable declarations are statements, right? Okay, so I did a little bit of nonsense here. So this is basically the approach. But of course, for parameters, you don't have to do any work because they've been pushed on the stack and then our function has been called. So like we saw that back here where it says it passes some parameter, I think. Yeah, and then so we push the last value that we push becomes our parameter, of course. So in this case, we actually do some maths on it. The result of the maths ends up on the stack again. And then we pass that on. Why is it unhappy here? Oh, what? Instruction compiled code. Oh, right. Second, we're actually trying to pass the function definition, not the pair with the function name. That's why I was unhappy here. Sorry, just another typo. Okay, so we'll save that for later. No, actually, we can just rewrite this. So we say curse statement in statements. All right. And now we see statement has a return type, but that's not really the kind of type we need in this case. But it has a kind, and that is what we want to switch on. So let's just Switch on the kind. Delete all of this again. Oh, actually, could have kept this line, I think, because it's... Okay. Anyway, so we loop over all the statements we have, switch their kind, and I would somehow like my autocomplete to work. Ah, now it comes. Create missing switch case. So we have a variable declaration. And now here is where we do switch curse statement type case what type are you? Type, built-in type. Come on, you can auto-generate. Code generator, hello. Okay, it's just built-in type. Okay. Ah, now you are there. Okay. And now we have that again. Now we just go for int32. Push int. And now if we look at... Do we have a variable declaration in here somewhere? I don't think we do yet. In the code we're parsing. No, we do. Double foo 1.5, right. Oh yeah, here, variable declaration. Double foo contains a literal as its argument. So I actually have to remember how I designed this here. But so we still need the value to be pushed for this variable declaration. And that we can do by looking at curse statement parameters. So let's see, we need an int32t initial value equals 0, and we write that here, initial value. And now if we have parameters, because I think you can just declare a variable in this language without giving it an initial value. Or it's only an int16. That's of course a bit of a design flaw in our program, but I'm not going to go deeper into that our instructions cannot contain larger values, you would have to address that. Oh, hi, good morning, Tony. How's it going? Yeah, it's going reasonably well. I made a few mistakes already, but I'm managing to generate some code, I think. The objective of this is that I've done some tutorials on YouTube. One is the bytecode interpreter, and one is the simple parser. And now I'm taking those two and using the simple parser's syntax tree to generate bytecode for the bytecode interpreter and running it. And so far we've set up the CMake project so we can build one app that contains the code from the bytecode interpreter and the simple parser. And now we're starting to actually walk the tree containing the syntax. And so right now we're handling a variable declaration, and this variable declaration will generate different instructions to reserve space for a variable. So here it will push a pushInt instruction with this initial value. Now you see our case is int32, but our instruction actually only contains, I think, uint8, uint8, and int16. So we can't really push a full 32-bit value. There are ways around this, but I'm not going into that. Like, the easiest way, of course, since you're defining your own bytecode interpreter, is just to make sure that one of the parameters in your bytecode interpreters is a 4-byte value, that you can just store it in the instruction. Another one would be to just put at the end of your program a data section and just put all these larger numbers in there, and then here have an instruction that is pushInt with relative offset, and then just specify the offset to the end of your code and to the right integer back there. Something like this. So there are ways to work around this. That's usually how you handle strings. You just have data stored somewhere, usually just after the end of your code. So that's something you could do here. Okay, so we have current statement, parameters 0. And now that, all right, in this code we actually have a double non-int. So I think I should replace, like, the example we used for the parser really does a bunch of things that we're not going to get around to. So I should probably write code that is equivalent. So like here, this is, yeah, this is actually the code that is equivalent to the code that the bytecode interpreter is running. So we should probably use this as our test file. Or rather not this, but like this. Something like that. But anyway, it doesn't really matter right now for teaching you because I don't think we have enough time left to actually run this code. Let's see what. So this needs to have the same type. So I don't know. For now, usually you would print an error or something here. Assert mtype equals curse statement type. So this is just, it's a bit, might be a bit unobvious. So, we have built this. If you look at our variable declaration here, the variable declaration is just one of many statements, and arguments are also just statements that are either function calls or, in this case, a literal. We've just lumped this all together into the concept of statement. So we know we have a literal that has the same type, and that's what I'm checking in this assert. And a literal has its number as the name, or its value as the name, apparently. So that means we need to do let's see. Initial value parsed, I guess is what we'll call this, just so we have less work. Okay. And now we say initial value parse name. And now we need to turn this into an integer. So string to int is really what we want, yeah. So we set our initial value to converting this string here. So usually in a slightly fancier parser, you would have a data structure that can store, for example, an int. And then what you would do is you would just take that int out of there. We've kind of made that parser just grab everything as a string and mark it as this is a string that is actually an integer, or this is a string that is actually a double. So not really so yeah, that's just something we did to make it easier for ourselves. So of course now we have to take this string and actually turn it into an int, which our tokenizer, I guess, should have already done. It doesn't really matter where we do it, but like in a cleaner design, that would be what you would do. Okay, so now we're actually done with parsing variable declarations. So the only thing we have to do here is right now we can generate invalid code. So what you usually do is you would handle all the variable declarations at the start of your program. Because or would you need to? Well, so here's the thing. You know, you use the same stack for variables and for temporary values while you're doing a calculation. So, you know, if you're adding two variables together, you will first push the first variable, then the second variable, and then you will run the add instruction, which pops those two values off the stack and pushes the result on the stack. So this is a temporary value that, when you need to use it, will get popped off the stack again. So you cannot have variables on the stack following this temporary value. So all your variables need to be front at the top of your area, of your stack frame, as it's usually called. So like the area of your stack that your current function uses. And then you need to put any temporary values that are just for the current calculation behind that. And so really what we should do here is, so I'll not fill in the rest here right now, because for one, I think our bytecode interpreter right now can only do integers. Our parser can do some things that our bytecode interpreter can't do yet. All right. So really, we should just ignore all the rest. Default, ignore. So, first, create all variables based on variable declarations. All right, and so, yeah, that's basically it. Now, you may know that, for example, here, I'm actually declaring a variable and doing a function call. Now, you cannot front load this function call because, you know, it might not be, I might be doing something up here that, you know, requires, that needs to happen. You know, I might be, for example, preparing the parameter for fopen here or something like that. So you don't want stuff to happen out of order. So what would you do to prevent this? Well, the thing is, usually what you would do is either you force in the parser already, you enforce that all variable declarations are at the start of the function, which is what classic C did. So I think it was, I don't even remember what, C99 or something like that. What was the last? Well, anyway, so I think that introduced the ability to just randomly declare stuff here. C++, of course, did it as well. 98, C98, I think is what it is, right? I don't remember. It's not really important. So what you would usually do is you would loop over this and not only look whether it has a value, but you would of course here check that this value is actually a constant and not actually grab. So you would say if initial value parsed kind equals what is this statement kind? Literal, yeah, okay. Somehow the autocomplete didn't do that. Kind, wait, no. Kind, literal. So you would check this and only front load the initial value if it's a literal. And then later, when you actually go over and so now you do a second loop over the statements. To actually generate the code. Now you have safely generated all the variables ahead of time. So what this does is it only takes the constant variables and initializes them, and if they're not constant, it just initializes them with 0. So we have reserved space for all our variables. And then we loop over the stuff again and actually generate code for the non-literal variable statements. Now, depending on how you write your parsers, what I usually did in my parsers is that variable declarations, like when I parsed a variable declaration statement, I actually pulled out these literal statements and just put them at the top, like in their own list. And so I didn't have to loop over all statements here again, but rather I just had this smaller list of variables. And I would actually only generate a statement proper for a variable declaration for the other kind. So you can do that during parsing already, and then it's a little cleaner. And that's especially good as you need to clean up. So you need to generate the code that frees all the memory used, all the stack space used, like pops all of these off the stack again at the end of your function. And so how do you do this? Well, one way is to just say num int variables equals 0, and then here say, reserve space for an int variable. So you could do this. And then after the code somewhere, clean up stack space reserved for variables, you would say for int x equals 0, x, whoops, less than num int variables plus x. And then here you can just say hop int so now you have these, but of course you need to do this for every type of variable. So if you have different types of variables, which again, as I said, our bytecode interpreter actually only handles ints right now, so we're fine. But if it handled other types, this would not be enough. And so there it would really be useful to just have that separate list of all variables that exist and need to be reserved. And then you could just loop over that list again to clean them up again. And each one can have their own type. So you can just, you have all the information there. And you can pop like one integer, then one string variable, then one integer off your stack. Not a problem. So yeah, that would totally work. But for now, we're taking this shorthand with just remembering the int variables. But so basically, this is the epilogue, and the other thing is the prologue. So since this is the epilogue, let's also generate our return instruction, since that will always go there. And now you might see what the problem is. We generate first a bunch of instructions to reserve space for variables. That's fine. Then we generate a bunch of instructions for the actual behavior of our function. And one of these instructions, or several even, might be return statements. And they then need to jump back here. But we haven't actually generated this code because this goes at the end of the code. And so until we have written all the code, we do not know how much code it is and at what offset the function epilogue that cleans up the variables and runs the return statement, at which offset that code will end up being. So what do we do? Well, the advantage is we only need to know the offset, but an offset, no matter where it points, is always the same size. Like a jump offset here in this bytecode interpreters is limited to 16 bits. So what we can do is we can first we can create the missing switch cases here. So we can write out an instruction with 0 in this offset, and then just make a note that we need to fill in that value there. And how we do this is by having a list. Like, we already remember the number of int variables we have, so now we have a standard vector I guess we can use int 16. Let's just say return instructions. And so now, whenever we parse a return instruction, we just put its index on there. And now here, at this point, we know at which offset the cleanup code will be generated. Cleanup code offset equals compiled code size. Wait, we have to do times size of instruction here. Because I think we're dealing with byte offsets here as far as I remember. Okay, and now we loop over 6T, I guess is enough. Now we can just say auto, who cares? Return instruction index in return instructions. And now we can say compiled code return instruction index p2 equals cleanup code offset. So basically we had the original, and these are not actually return instructions, that might be a bad name. They are return commands. But it's the jump instruction. So we should probably refactor, rename return, whoops, command jump instruction index, and here refactor, rename return command jump instructions. And yeah. And so now when we're parsing a return command, we'll just remember each of the jump instructions that doesn't yet know where to jump to. And then here at the end, we fill those out with the actual offset of the cleanup code. And then here, we clean up the variables and then perform the actual return from the function. So now, one more thing here. This is a special case that I'm writing here for returning. We can and probably will, but not today, make this more generic. Because there are many cases in code generation where you are still to generate code. So what you can do is you can have a table, maybe with names or some sort of unique identifier number. And so you just say, I will later know this address. And then you just have a list of instructions that need to jump to this address. Then keep them under that special name. And then later, when you actually know the address, you can just say, now do it for all instructions saved under this name. So this is a general procedure that you can wrap in a nice little class, basically. Yeah. Okay, so that's the general approach. And I think I will finish the stream here because we have about 15 minutes left, and I don't think we'll be able to do much in that time. But yeah, it's we're at a good stopping point here. Because what we've now done is we've shown how you, in general, roughly generate code for a simple function. You generate the prologue, which means mostly reserving space on the stack. Then we generate code for each individual statement, which we can do recursively. We can show that next stream. And then, of course, you generate the epilogue and fill in any instruction that needs to access the epilogue. And of course, the general way how you work with your code is just your parse tree contains a list of functions or whatever your top level constructs are, and you just loop over those and call a function that generates code for each one. And now at the end we will have a compiled code array that is equivalent to this code array. It's just a thing that contains instruction structs filled out. As we've said in our bytecode interpreter tutorial, instructions are really just structs that describe what to do. It's not magic. One thing, what did I want to say? I just thought of something. Oh yeah, one thing you may notice, why am I working with indexes of instructions here? And the reason is because I have this compiled code array, and every time I add an element, it may need to make its pointer, its memory block that contains all the elements. It may need to make that larger. And if it can't just add a few bytes at the end, because there is another memory block following it that it would collide with, then it will allocate a completely new block that is larger, will copy all the instructions into that, and then append my new instruction. So that means whenever I add an element to a vector using pushback, like here, all the addresses in this to all the individual instructions that I might keep become invalid. Or may become invalid. Like, of course, if there's enough empty space following my memory block, then it will just leave them in place. But you don't have a guarantee for that. If your memory is really full, then it will constantly be shuffling things back and forth. And so that's the reason why, in this case, you always want to keep all your information in either offsets, byte offsets, or in indexes to instructions. And then you can always later translate them once you're finished. If you need to. And that's the thing, code should not be modifiable either, so that's not really a big limitation. But yeah, I apparently seem to have lost these arguments. That's interesting. I mean, we're not using any of the arguments there, but I usually like to have them declared because I might want to add some sort of compiler switch. Although we shall see, we probably won't need it. Anyway, that's pretty much it. So I guess next stream we'll continue with actually generating code for everything else. So we will be generating function calls. Literals, of course, shouldn't occur here. So function calls and operator calls. And of course, you would handle variable declarations here that do not just consist of a constant literal value. Those are actually pretty easy to handle because all you do is you handle them like what their value is, which is either a function call or an operator call. Because we've already established, we've already done all the literals, so those can be ignored. But basically you just generate code for the value because you've already reserved space for them up here. So that's nice and easy to handle. All right. Thank you for listening. Yeah, I mean, I've been going 1 hour and 50 minutes, so yeah, I guess I'll be ending here just because this is a good spot to end at. I mean, if you have questions about programming language, I mean, for those of you who came in late or something, I guess I can demo you the bytecode interpreter and the parser. So the parser, simple parser here, just loads a text file into a variable, into a string actually, then runs a tokenizer of it to turn it into tokens. We can whoops. Yeah. And then we actually debug print all these tokens now. And then it parses them and debug prints the parse tree. So if I run this, and wait a little moment. Oh, yeah, of course it can't find the file because the file path that I hard-coded here is actually from the other computer. And we are actually inside Parser and compiler. So this should work now. Yep, okay. And now if we look at what it did, is so it read this text, void main. We don't have pointers or anything yet in this parser, so it's just char argv. Variable declaration double foo, printf with a string and a mathematical expression. And then you see here it's split it up into tokens. Void main opening bracket is an operator. Others are identifiers. So that all works. And then here it actually generated a syntax tree, which of course is a slightly flat tree. We have a main function with those two parameters, and as you see, it turned the types into their canonical names. So I only specified int, and here it says, oh yeah, signed int, signed char. And then all the statements for that function. So we currently handle variable declarations just like any other statement at the parser level, just to make it easy. So this is the double foo that we had, and a literal is also just a statement here. I didn't want to start a new data type in this parser because the parser was just supposed to be a fast example to get you to a point where you understand how these work. So yeah, there it says literal double 1.5. So we just remember that this is a number 1.5 as a double. And then here for the function call, that is not a double but actually a void, and it's called printf, and then takes as an argument this literal. Oh yeah, right, these brackets are just because a literal in theory could have, like, since I use the same data type for a function as I use for a literal, it just adds these parameter brackets, even though a literal of course doesn't have parameters. It's a terminal node basically. And then here is the mathematical expression with an operator call for minus. It doesn't declare a return type, so that's why it says void here. And then here is a signed integer 2020, and the other stuff is a plus operation, and you see it handled operator precedence already. So the multiplication operator here grabbed both its arguments, even though the plus operation for 2020 was first. The plus operation for, oh no, that plus one, the minus, I mean, was first. But still, you know, so operator precedence actually already works. But if you want to exactly know about this, check out my YouTube. There is a playlist of, I think it's called C++ programming. And that has the tutorial where we write the simple parser. And then we also have the bytecode interpreter, which basically generates an array full of instructions. So it generates a bunch of bytecode and then just runs them. Oh, it actually passes a parameter to it, so that's something we do as well. And so if you run this, it doesn't quite look as impressive because this is a static calculation that just runs 6 times. And then we return the result. But you see it ran the code, number printed. I think we have a special... Where is it? Print int here. Yeah, that's the number printed statements. So anyway, that's it for today. Apologies if that was shorter than you hoped. And hopefully we'll have a continuation of this stream next week. Again, I will keep Discord and the schedule under this Twitch stream updated with which day which stream will be. Hopefully I'll see you then. Thank you for being here, and bye bye.